Hi guys. So far we've talked about three examples of discrete random variables. The first is a Bernoulli trial. So we run a trial and it succeeds with probability p and it fails with probability 1 minus p. And then if we want to run n trials and we find the probability that k trials succeed, that's a binomial random variable. So what's the probability that k successes occur in n trials? And then we took the limit of a binomial random variable and got a Poisson random variable. So those are the three we've looked at so far. And today we're going to look at two more. So for the first example we're going to look at, suppose the question is, or say that x represents the first success. So what is the probability that, so x is the trial that gives us the very first success. So in this example, trial 1 fails, trial 2 fails, trial 3 succeeds, 4 fails, 5 fails, 6 succeeds, and so on. And so in this example, x would equal 3. Because trial 3 is the first trial that we got a success. So how many trials do we need to get one success? And let's see, the probability, so if k is bigger than or equal to 1, so we don't know how long this could take. K could go up to infinity, technically, right? It could be the 100th or the 1000th or the 1,000,000th trial before we finally have a success. We don't know. So k could be arbitrarily large, but of course we have to run at least one trial to get one success, so k can't be 0, unlike the binomial. That doesn't make sense to have a success on a 0 with trial. So for k bigger than or equal to 1, what's the probability that x equals k? And the probability that x equals k, well, let's look at the example. So the probability that x equals 3, we fail, success. So the probability that x equals k is the probability that the first k minus 1 trials fail, and trial k is a success. Right, so for x to equal 3, trials 1 and 2 must both fail, otherwise x would have been 1 or 2. So 1 or 2 fail, and then 3 has to be a success, and that's the only way that x equals 3. So for x to be k, we have to have k minus 1 fails in the first k minus 1 trials, and trial k is the only one that's a success. And because these are independent trials, it's going to be 1 minus p. That's the probability that they fail, and then we have k minus 1 fails. And then we have one success, which we multiply that by a p. And now we don't have any n choose k sort of thing here, because there's only one order that this can happen in. You can't rearrange the order. Right? There has to be f's on exactly the first k minus 1s, and then the s has to be exactly on the kth trial. So this is the only order in which x equals 3. So that's the probability that x is 3. Or sorry, that x equals k. And this is called a geometric random variable. So x is a geometric random variable. So that's the name. Okay, so what's another random variable we're going to look at? The other example I'm going to do in the videos is the negative binomial. So the geometric asks, when is the first success? But the negative binomial asks, when is the rth success? So let's change this a little bit. So we'll say rth success. So if r equals 3, suppose r equals 3, this means we're looking for the first trial in which we get the third success. So we want to know, when do we have a third success? Then x in this example would be, well, here's our first success, our second success, our third success. So x equals 7 in this example. Okay, so for a fixed r, So suppose, if r is 1, we just have a geometric, right? Because that would be the first success. If r is 2, we're looking for the second success, which would be 6 in this case. But let's fix an r and say we're looking for the rth success. So for a fixed r, and so what could k be? Well, k would have to be at least as big as r. It could be arbitrarily large again. If r equals 3, it could go to 1,000 or 1,000,000 or 1,000,000,000 or something. But it takes at least 3 trials to get 3 successes. There's no way you can have 3 successes in 2 trials or 1 trial. Right? So you have a k bigger than or equal to r, then the probability x equals k is, well, now then we've had r successes, right? So we're going to have p to the r, because p is the success probability, and we've had r successes. And then we'll have 1 minus p to the k minus r. Okay, so now then this gives us, so in this example, say, we are looking for the third success, which would be this one. So we've had 3 successes, so we have a p to the 3, and then we have 4 failures, so we'd have a 7 minus 3 to the 1 minus p. So that just counts the number of failures we've had and multiplies by this probability. Now, in the geometric distribution, everything before the s was f's. So it didn't matter how you rearranged it, it's all just f's. They all have to fail. And there's only one way they can all fail. But now then we have 2 successes. And it actually doesn't matter in this example, they're the 3rd trial and the 6th trial. But it could have been that the first trial was a success, the second trial was a success, and then we had failure, 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 and then the 3rd success was on the 7th trial. And it actually doesn't matter which 2 trials that the first 2 successes are on, as long as the 3rd one is on the 7th trial. So we have to count the rearrangements of these letters. So here, we have to look at the rearrangements of everything that happens before that last success. So how many letters are here? Well, if k is 7, then we can't count the last one. So the last one has to be a success. You can't rearrange that. But we can rearrange everything before that last success. So we're going to have k minus 1. And then we're going to choose, if we're looking for the rth success, so for the 3rd success, the last one has to be the 3rd success, so there's going to be r minus 1 successes before that. So we're going to choose r minus 1 places to put those successes. And so this is the distribution for x, if we're looking for the kth success. The probability that the rth success. The probability that our rth success is on the kth trial is 1 minus p to the k minus r, p to the r, and then k minus 1, choose r minus 1. And this kind of random variable is called negative binomial. So x is a negative binomial. Or I should say maybe x has a negative binomial distribution, to be a little less careless. Okay, so these are the last examples of discrete random variables we're going to do. I've got a little more time, so maybe let's look at the geometric a little more closely. So the geometric. Just a special name for the case where we're looking for the first success. And our random variable is going to be x. So the probability x equals k is 1 minus p to the k minus 1 times p. So we have k minus 1 failures, and then our kth trial is our first success. And that only counts for k bigger than or equal to 1, being a natural number. So I guess that's another way to think about it. You could think of it as for any k in the natural numbers is equivalent. Okay, so one thing we know about random variables is the probability of a random variable occurring, well, for probabilities anyway, the probability of the whole space has to be 1. right? So if x is going to take on the values from 1 to infinity, then we should have that the sum from k equals 1 to infinity of the probability that x equals k is equal to 1. So let's go ahead and check this and make sure I haven't defined something that doesn't even exist. So maybe this isn't even possible. It's not an actual random variable. If it violates the laws of probability, then we're in trouble. So let's make sure I haven't violated the laws of probability. So what is the sum from k equals 1 to infinity of the probability that x equals k? Let me go ahead and write down here. This is a check that. So I'm not just claiming this. Right, this is something we want to show for ourselves. So let's start here on the left-hand side and derive the right-hand side. So I start here. Here's the sum k equals 1 to infinity of the probability x equals k. And the probability x equals k is just this by definition. So it's the sum k equals 1 to infinity of 1 minus p to the k minus 1 times p. Okay, there's only one part of this that depends on k. So we have a 1 minus p to the minus 1 and a p. We can pull that out. So we have a p divided by 1 minus p times the sum k equals 1 to infinity of 1 minus p to the k. And now this series should be familiar to you. This is the geometric series. If we have the absolute value of r less than 1, then the sum from k equals 1 to infinity of r to the k is r over 1 minus r. So this should be familiar from Calculus 2, I think. Calculus 2 or Calculus 3 or whichever class they teach that in. And so we're going to apply this. This is where the name comes from. So we call it a geometric distribution because the distribution looks like a geometric series when we start adding up the terms. And so let's plug in this formula. So we have p divided by 1 minus p times, and now then our r is 1 minus p. So, I mean, unless 1 minus p equals 1, if p is 0, then of course you're never going to have a success. Otherwise, 1 minus p is less than 1. And then we just plug in this formula. So it's 1 minus p divided by 1 minus p. And this is equal to p divided by 1 minus p times 1 minus p over 1 minus 1 plus p. So let's just distribute the negative through this parenthesis. And this is equal to, well, I can cancel this 1 minus p and this 1 minus p. So I have p divided by, and 1 minus 1 plus p is p. So this equals 1. And so, in fact, the probability is 1, and we're not breaking the laws of probability. So in class, we'll probably compute the mean and variance of the geometric distribution, and we'll look a little more at the negative binomial distribution. All right, God bless you guys. I'll see you soon.